Okay, here we are. Good morning, everybody. This is our February CMCC webinar meeting. I'm Enrico Scoccimarro from the ClearUp division at CMCC, and I'm pleased today to introduce you Gabriele Accarino, that is going to show us the recent activity that they performed in the Ask division, the division that we have in Lecce for advanced scientific computing. And we are going to talk about enhancing tropical cyclone localization through machine learning approaches, but we will be back on this soon. Just give me 3 minutes to introduce first the CMCC. As you know, we are a global scientific institution. We are mainly focusing on the study of climate variability and change and its effects on the society. Our mission is mainly to investigate and to model the climate system and its interaction with the society. And this is something that we try to do, providing a scientific result to stimulate the sustainable growth and also to protect our environment and to drive adaptation and mitigation policies in a changing climate. This is something that we are doing since, I would say, 2007, when CMCC was born, and we are now distributed in the Italian territories with different offices in Milano, Venezia, Bologna, Viterbo, Sassari, Caserta, and Lecce. And this is also the network from which we started, because most of the actual partner, the member and institutional partner that we still have, and this number also increased in the past year, is also partially the one that we had at the beginning of the CMCC consortium. So we have a university from Milan, Bologna, Salento University, Sassari, and also there are other institutions, research institutions, such as the National Institute of Geophysics and Volcanology, and also the non-profit group Research for Future from the US. As probably some of you already know, the CMCC recently entered in a new phase. We are now in 2024. The CMCC has been somehow redesigned, and we have now 3 main institutes: the Institute for Earth System and Prediction, the Institute for Climate Resilience, and the European Institute on Economics and the Environment. These are the 3 institutes in which all of the research division that we have at CMCC has been belonged to, and there is now the different institutes are now representative of CMCC activity in terms of collaboration and exploiting the advanced technology and whatever we do within CMCC. Also, thanks to our supercomputing center, that is the one located in the headquarters in Lecce, most of our activity are mainly possible thanks to these capabilities, and the CMCC supercomputing center is one of the most powerful computation facility in Italy and one of the more advanced in Europe, fully devoted to climate change research. And that it is also thanks to these capabilities that we are able to investigate what Gabriele is going to show us. Before giving a short introduction on Gabriele, just to say that you will have the possibility to interact. At the end of the webinar, you can put your questions in the Q&A section, and then I'll read the question to Gabriele and he will answer. And then there is also the possibility to raise your hand. This is up to you. If you prefer to speak, you can speak, and that's it. The idea is to have more or less 30 minutes of presentation by Gabriele, and then in the end, we can spend 20-30 minutes to answer your questions. Well, going directly to the object of this webinar, today Gabriele is going to show us something that is, I would say, really integrated in what CMCC has been involved in the past, would say 15, even more years, because the research on tropical cyclones started at the beginning of the when CMCC was formed. At the beginning, it was one of the first research lines that we had here. But now, in addition to the typical studies that we tend to do on tropical cyclones, we are trying, and Gabriele is going to talk about this approach, trying to put the effort and experience of the machine learning group that we have in Lecce, that is led by Gabriele, to try to put together the knowledge of machine learning approaches and the knowledge that we have on the dynamics of this system in Harvard climate model and reanalysis to try to put together these experiences and to gain something in terms of ability to track and forecast this kind of events. Gabriele is a computing scientist. He has a background and a PhD on environmental sciences and is working with us since many years, I would say. And he's been involved in many activities related to the evaluation and the application of machine learning tools to the detection and prediction of extreme events. So tropical cyclone is one of these kind of events. And Gabriele, please, the floor is yours. You have more or less 30 minutes, okay?
Okay, thank you, Enrico, for the introduction. I'm going to share my screen. Okay. Can you see it correctly? Okay. So, good morning, everyone. My name is Gabriele Accarino, and I am a junior scientist within the Advanced Scientific Computing Division of the CMCC Foundation. And during this presentation, I will show you a machine learning application aimed at localizing tropical cyclone centers in climate data, relying on a deterministic trigger to reconstruct the trajectories. It is well known that tropical cyclones are among the most spectacular and deadly geophysical phenomena. These extreme events usually result in severe disasters and the loss of lives. Just to give you some numbers, in 2005, Hurricane Katrina resulted in over 1,200 recorded fatalities in regions of Florida and more than 125 billion in damage. So it's clear the reason why substantial resources have been devoted around the world to the study and forecast of such extreme events. Machine learning has emerged as a powerful tool in addressing various aspects of tropical cyclones analysis and prediction. Machine learning algorithms are being increasingly applied to tasks such as detection, localization, and forecasting of these extreme weather events. While detection involves determining the presence of a tropical cyclone in input data, localization aims at identifying the geographical coordinates of the cyclone center. Another important task is tracking that allows reconstructing the cyclone's trajectory over time. This task is closely related to the localization one, and it is traditionally achieved through the adoption of deterministic tracking schemes. These schemes are typically based on subjective thresholds and rules set by the scheme's designer to identify and track cyclones on numerical simulation outcomes or reanalysis data. Addressing the tracking task directly through machine learning is intrinsically challenging. That's why in this first study, we mainly focused on localizing TC center position in ERA5 analysis data, further relying on a deterministic tracking scheme to join detected TC centers along a potential trajectory. This slide formalizes the proposed localization task. Basically, we want to find a functional mapping F between a given set of atmospheric conditions at time t provided as input and the actual TC center location at the same instant. Actually, we don't know what this function looks like, but we can estimate this mapping. In particular, machine learning, especially artificial neural networks, can help to learn such potentially complex mapping directly from available data. This relationship is parameterized through a set of weights and biases, here indicated with the theta, that are learned during the training process. What we get is a TC center location prediction, here indicated with L hat, that we want to be as close as possible to the observed TC location at the same instant. It is worth noting that this approach does not require having the history of past TC center position. The tropical and subtropical waters that support the formation and development of cyclones are called cyclone formation basins. Globally, there are 7 such basins, and the Northwest Pacific is considered to be the most active in the world. The most active period is September, and the least active one is May. Roughly 19 tropical cyclones develop globally each year over ocean water whose surface temperature exceeds 26 Celsius degree. But they often move out these regions into higher latitudes. In this study, we retrieved tropical cyclone information from the International Best Track Archive for Climate Stewardship dataset. IBTracks is indeed an institutional, open access, and centralized archive that provides the most complete set of historical TC best track data on a global level from 1841 to present. It integrates historical records with observations retrieved from 12 different meteorological agencies worldwide. Concerning the geographical domain, this study mainly targets the North Pacific Formation Basin, which is widely recognized as a particularly active region where most TCs occur every year. But since a substantial number of TCs events cross both the North Pacific and the North Atlantic regions, the final domain of interest is the one highlighted in green, namely the joint North Atlantic and Pacific Basin. So, starting from IBTracks, we select the TC records in the following way. First, we considered only TCs occurred in the 1980-2019 period at a 6-hourly temporal resolution and belonging to the joint North Atlantic and Pacific Basin, as previously described. Then only records whose track type field was flagged as main were considered. Therefore, we implicitly discarded the provisional, spur, and provisional spur records, meaning that the corresponding values have not been reanalyzed yet and therefore are of lower quality compared to main tracks. As an additional selection step, tracks were filtered out based on nature field, specifically discarding those trajectories marked as not reported, whose nature is unknown, disturbance storm that correspond to not well-formed storms, and mixture that correspond to tracks that received contradicting reports about the nature of the observing system. At the end of this filtering and selection process, only tropical storm, extratropical, and subtropical storms tracks were considered. This figure reports the visualization of 6-hourly tropical cyclone center location within the 1980-2019 period in the joint North Atlantic and Pacific Basin. TC location in each sub-basin are highlighted by different color, along with the relative number of occurrences And only Ibitrax records whose nature is a tropical, subtropical, and extratropical storm are shown in this picture. Climate variables are the main drivers that contribute to the formation, strengthening, and fading of TCs during their lifetime. In this study, climate variables were retrieved from ERA5 reanalysis on single and pressure levels datasets. ERA5 combines global numerical weather predictions with available observations in an optimal way to produce consistent estimates of the state of the atmosphere. We considered 6 predictors of TCs according to the studies of Zhao and Scoccimarro. They were provided on a regular grid of 1/4 of a degree of spatial resolution, targeting the geographical domain previously described, and ERA5 maps were managed as 2-dimensional maps of 280 pixels times 880 pixels size. Moreover, data was collected with a 6-hourly temporal resolution for the period 1980-2019, thus matching TC records previously selected from Ibitrax. ERA5 maps were evenly tiled into 7 × 22 non-overlapping patches, stacking together the 6 input drivers, and this results in patches of size 40 × 40 × 6 pixels each, in which the TC can occur in every position, not necessarily at the center. Latitude and longitude coordinates were extracted from Ibitrax and associated to each patch containing a TC, here highlighted in green, taking care of converting such coordinates to local X and Y pairs. Patches that do not contain a TC, referred to as negative patches, were labeled with a negative coordinate, in this case -1, -1. We also selected the 3 corner patches closest to the storm center as negative patches, here highlighted in red, plus an additional one randomly selected across the domain, here highlighted in yellow. We iterated this procedure over maps belonging to the training and validation years over the 1980-2019 period. But for the test set, we selected the 2 consecutive years for each decade, namely 1983, 1984, 1993, 1994, and so on. And beyond pages that contain a TC, all the remaining ones were considered as negative pages. This slide depicts how an input page looks like. The spatial dimensions consist of 40 pixels for both X and Y axis, meaning that the local coordinates range from 0 to 39. The 6 climate variables were stacked together along the depth dimension. Latitude and longitude coordinates of the TC center were retrieved from Ibitrax, and they were converted to 0, 39 local coordinates. In the case that TC is not present within the input patch, we label local coordinates with a couple of negative values, -1, -1 in our case. So first, we split the available patches into 70% for training and 25% for validation purposes. We found that the number of patches containing a TC is 4 times lower than those that do not. To address this imbalance ratio, we applied the left-right flip, up-down 180 degrees rotation only to positive patches as a data augmentation procedure. The test set is highly imbalanced with respect to training and validation sets, but we didn't apply any augmentation technique. in order to evaluate the performance of the proposed approach in a real case scenario. Before training, we scaled the 6 input predictors in the 0-1 range, so they have the same scale. In this slide, the basic BGG architecture adopted for the localization task is depicted. As you can see, input patches are processed by convolutional and max pooling layers that extract spatial invariant features, progressively decreasing height and width dimensions, while at the same time increasing the depth of the activation volume. After the convolutional blocks, the resulting output is flattened and processed through a series of dense layers that gradually reconstruct the information and links it with the target represented by the local XY coordinates of the TC center location within the input patch. Two different loss functions were implemented and used for training such machine learning model. The first one is the mean absolute error between real and predicted coordinates. The second one is a custom loss specifically defined for this study called Cyclone classification localization loss, which is a linear combination of the mean absolute error, the binary cross entropy loss, and the Euclidean distance between real and predicted coordinates. The Cyclone classification and localization loss tries to achieve two goals at once. First, minimizing the classification error through binary cross entropy, and second, minimizing the localization error through the mean absolute error and the Euclidean distance terms. Considering the basic BGG architecture showed earlier, a total of 4 different architectures have been assessed for the TC localization task, called BGG version 1, version 2, 3, and 4, which basically differ in the convolutional block complexity in terms of composition and number of parameters, as you can see in the left part of this slide. But starting from such 4 BGG architectures, a total of 13 machine learning models were trained for the TC center localization task. Each model differs in terms of the hyperparameters configuration, for example, the loss function, the kernel size, as you can see in this small table. These parameters were used in the training stage. However, all the models were trained for 500 epochs with a batch size of more than 8,000 pages with a learning rate of 10 to -4. Okay, so since the 13 models are trained with a different set of hyperparameters and/or layer configuration, each of them learns different characteristics and high-level features in the training set pages. Therefore, an ensemble approach has been assessed in this study to combine the predictions made by different machine learning models with the aim of improving the overall accuracy skills. For each batch of the test set, the approach consists in evaluating first how many of the 13 machine learning models agree on classifying the presence of the TC. An additional hyperparameter M in the figure was introduced to define the minimum level of consensus among the 13 models about the presence of a TC center in the input patch. This value depends on the ensemble size and was set to 7 to have more than 50% of models in agreement. Each of the 13 models can potentially provide very different estimates about the location of the TC center in the same input patch. Therefore, the interquartile range method was adopted as a further filtering step to keep only the estimates closer to their median value. The method consists in considering as outliers those TC center estimates, here reported as X, that satisfy the inequality reported above. Then the localization of the TC center is performed as the ensemble average of the XY estimates of inlier. This slide shows the machine learning ensemble approach applied on a specific time instant of the tropical cyclone John evolution. In particular, we are focusing on the 15 August 1994 at 6 a.m. In panel A, we see the TC center estimates of the 13 machine learning models, red squares, that reached the consensus. The background is the mean sea level pressure variable. All the 13 models agree about the presence of the TC in the input patch and exceeded the minimum level of consensus required. The blue cross here represents the actual TC center position, whereas the green diamond is the average TC center position provided by the 13 models as the machine learning ensemble. In the center panel, the interquartile range approach is applied to refine TC center estimates. The IQR bounds are highlighted by the big red square, and as you can see, two TC center estimates are detected as outliers. Panel C depicts the final stage in which the outliers are removed and the models participating in the ensemble go from 13 to 11. The ensemble TC center estimate provided by the remaining 11 model is highlighted by the purple triangle, showing that it is closer to the actual TC center position, which is the blue cross. Indeed, this allows lowering the Euclidean distance from 62 kilometers to 39. So after predicting TC center locations by means of the machine learning ensemble approach, a hybrid tracking scheme was proposed to joining together individual TC center detections over time to create potential trajectories. It is worth noting that in this phase, we don't need to access observations. The hybrid tracking scheme merges together machine learning-based TC detections with a deterministic tracker based on the work by Scoccimarro and colleagues. In the right part of the slide, you can see the two phases of the hybrid approach. In the first phase, for each detected TC center location, the scheme checks the presence of other detected TC centers after 6 hours and at a distance lower than 400 kilometers. If no TCs are found, the trajectory is complete. Whereas if multiple TCs are found, the closest one is considered belonging to the same trajectory. A generic example of phase 1 is depicted on the left side. So we are in phase 1, case 1.2, where at the subsequent time step, namely 12 o'clock, multiple TCs are found. Here they are indicated with the crosses. Therefore, the closest one within a distance of 400 kilometers is linked with the previously detected TC center, the one at 6 a.m. Then phase 2 is applied to mark the reconstructed trajectory as potentially valid. In particular, potential trajectories should last 3 days or more, having a maximum sustained wind greater than 17 meters a second during at least 3 days, not necessarily consecutive, over a region which is centered on the middle of the TC, whose spatial extent is 8 by 8 degrees. Now, once potential TC trajectories are reconstructed, we can match them with the observed tracks provided in IB tracks. In order to do that, we readapt the procedure described in board in 2022. More formally, we have detected track D, which is composed of endpoints at given times. And we have also observed the tracks from IB tracks that in a similar way consist of a collection of points at given times. Basically, the track matching algorithm associates each point of track D to those points of O that at the same time are closer than 300 kilometers from the point of D. Here, three cases can be distinguished. Case one, none of the points in the reconstructed track D match any point in the observed track O. And this is basically a false alarm. Case two, if all the points in the reconstructed track D shown as red points are part of some observed track O shown as green points, then the observed track is considered as the best match of D. Case 3. If the points in the reconstructed track D shown as red points are spread across multiple observed tracks shown as green and yellow points, then the longest observed track, the green one in this example, is considered as the best match of D. So the probability of detection and false alarm rate are used for assessing the track detection skills. These metrics are computed considering the TC tracks reconstructed by the hybrid tracking scheme just presented. Here, it refers to tracks detected from ERA 5 and actually present in IB tracks. Misses are tracks not detected from ERA 5 but present in IB tracks, whereas false alarms are incorrectly detected tracks that do not have a counterpart in IB tracks. This slide provides the evaluation of the hybrid trigger proposed in this work. In particular, the figure on the left compares the pod and far metrics of the hybrid approach with those achieved by 4 deterministic triggers from literature. The results of pod and far values have been readapted from Board et al. 2022 to match the geographical domain and the temporal period targeted in this work. We found that the pod value is almost identical to most of the deterministic triggers compared, while the far value is in line but slightly higher with the OWZ and track triggers. From a quantitative standpoint, the table on the right reports the values explicitly, and as you can see, the number of misses and hits in our approach is in line with the other triggers, but however, the number of hits is lower than the algorithm. Thus, we can state that our hybrid solution was able to produce nice results, deserving further development towards a fully data-driven approach. As a test case, I selected the tropical cyclone Keoni, which occurred from 9 August to 4 September 1993. As you can see, the hybrid tracker is able to closely follow the observed Keoni trajectory reported in blue that we retrieved from IB tracks. When the TC is classified as not reported in IB tracks, The spatial patterns of the variables from era 5 are not clearly defined, as you can see in the top right panel, and the accuracy of the TC center localization achieved by the machine learning ensemble is low. Indeed, the estimate is located about 67 kilometers away from the observation. On the other hand, when the cyclone is classified as a tropical storm in IB tracks, the spatial patterns of the input variables around the TC center become more evident, as you can see in the bottom right panel of the slide. In this case, the localization accuracy achieved by the machine learning ensemble is very high. Indeed, the error between the estimate and the observation is only about 13 kilometers. Moreover, as it can be seen in the figure, the approach estimates some TC center which are out of trajectory. In this case, the TC center has been localized in adjacent patches, which, even though representing a limitation of this approach, does not have a major impact on the overall trajectory reconstruction, as it still satisfies the thresholds of the deterministic tracking scheme used. The experiments were carried out on the CMCC supercomputing facilities, in particular on the Juno hybrid cluster, exploiting one node equipped with 2 GPUs for training. All the models were trained for 500 epochs, taking about 2 hours and 40 minutes on average each. The inference is performed in a matter of seconds or few minutes, when performed on an entire year of test data. It is important to noting that we used only one CPU for inference. This slide summarizes the strength and limitation of the study, and we found that the proposed approach is robust in localizing also out-of-sample TCs, especially those marked as not reported or disturbance, which were not included in the training set. The results can be further improved with additional models, trying also different architectures, and moreover, the inference phase is very fast, even with 13 machine learning models. Among limitations, we found an additional effort in fine-tuning the 13 models. And in addition, the patchwise approach limits the localization capabilities to one cyclone for each patch. In some cases, as I described before, TCs are localized in neighboring patches, but still satisfying the thresholds of the deterministic tracking scheme. Last, we rely on a deterministic tracker, so it is not a fully data-driven approach, whose investigation is left to future developments. This study was published in the AGU Earth and Space Science Journal, and it is fully accessible online. For this work, I would like to thank my colleagues and the Professor Giovanni Aloisio for their contribution to this study, as well as Enrico Scoccimarro and Daniele Peano for their scientific support. For this work, I acknowledge the inflows for HPC and the intertwin European projects that partially supported these scientific activities. So thank you very much.
Okay, thank you, Gabriele. And it is now time for questions. I see few of them online. Is there anybody interested in giving the question? I mean, an oral question, you can also raise your hand. Well, the first question is from Naveen Raghu. Silly question, but the need purpose of developing such as machine learning track characteristic from era 5 is to fill information on periods not covered by IB tracks before 1980.
Okay. Interesting question. No, actually, IB-Tracks cover the past tropical cyclones trajectory starting from 1841 up to present. And the idea around this work was to have a machine learning approach for detecting TC center location and to apply it on numerical simulations to provide tropical cyclones trajectories starting from the outcome of this numerical model simulation, as we did in, for example, in the flows for HPC, and as we are doing in the context of the Intertwin project, in which we aim at tracking TC on SMIP data. I know that is very challenging, but we will work on this.
Okay, so I think that I will. There are many questions. I will follow the approach of giving one question for the single user, and then I will be back on the second and third eventual question that each one will ask. There is a question from Giulio Boccaletti. Your VGG was a complex layering of CNN and other. What guided your choice of particular architecture?
Oh, well, thank you for this interesting question. Actually, we adopt the VGG architecture because it is a standard de facto in computer vision, because it is a very, you wrote a complex layering of CNN, but it is composed by multiple CNN and then a dense layer at the end. But I see the VGG as a more standard architecture, and we want to try a very simple machine learning model to carry out this task before proceeding with the more complex architectures. So it is a very, very basic VGG that we provided with different flavors, because we trained the VGG version 1, version 2, 3, and 4 by complicating a little bit the internal architecture, the number of convolution, and other stuff.
Okay. So now a question from Ronald McAdam. So, hi, Gabriele, thank you for the clear and interesting talk. You spoke about methods to overcome the problem of data imbalance in training data. Could you please comment on how commonly this is performed and if it can be applied generally to other climate extreme problems?
Okay, thank you for this interesting question. Actually, so we manage the ERA5 maps as 2D pictures. One picture for each variable. Okay, if you consider all the ERA5 maps together, this is basically a 3D tensor. Okay, because the time dimension is implicitly considered in this study. Okay, if you look at one patch of size 40 times 40 times 6, because we stacked together the input predictors, this is basically a 3D picture, a color picture, because in computer vision you have the x and y dimension, the spatial dimension, okay, and the channel dimension with the color information actually. So in order to address the imbalance ratio between positive and the negative samples, we pick this patch, this positive patch, because we perform this augmentation only on positive patches, and then we considered alternatives of this patch by flipping the patch. It's a very straightforward augmentation, so you can flip on the y and x axis, and then you can also rotate by 180 degrees the entire patches. And yes, you can use this approach to to augment your data in other climate science problems. But in this case, you have to take care about the label, because if you have a patch and the cyclones located in a different point of the patch, and then you rotate, you flip the patch, then you have also to update the coordinate of the TC center accordingly, okay? So in general, you can apply it, okay? But depends by the model, by the model. If you have something very specific, like some attention mechanism, you can, so it's preferable to not perform any augmentation technique, okay?
Okay, Gabriele, there are many other questions. I mean, please, let's try to stay in 2 minutes for each answer, because at least 5 more coming.
You know, Enrico,
Patrick,
thank you.
because we want to stay in 1 hour as a total. Patrick Uereza, how did you come up with variables that you choose? Had you tried other variables prior to making the decision which to use?
Okay, actually, we before starting this this investigation, we read a lot of papers from the scientific literature, especially those of Zhao and Enrico, and they actually used these variables for this for the tracking task, basically. And since the aim was to track trajectory with the deterministic tracking scheme, we used the same number of variables and the same variables, okay? And maybe it would be interesting, and I think that also Enrico agrees about that, trying to repropose the same approach, but with a lower number of predictors, to see if how the results change, okay?
Yeah, sure. This is an important point. I mean, one of the main problems that we have when we try to track cyclones in models and analysis and whatever is that we need to use multi-level, multi-fields, etc. So it would be nice to try to find a way to maintain the same skills but using less fields for the tracking procedure. So Leonardo Aragao is asking, thank you, Gabriele, for your excellent talk. Could you give some details on how your method identifies cyclogenesis? Since favorable atmospheric conditions do not necessarily result in cyclone formation, I wonder how your method differentiates a potential cyclone from an atmospheric disturbance.
Okay, thank you for this question. And actually, I said before during the presentation, we explicitly discarded the disturbance among other nature of other tracks, okay, other events based on the nature field, okay, from AB tracks. But on the test set, we tried to feed these events to the machine learning model, which surprisingly was able to capture and to produce a very accurate location of TC center, also for disturbance storm and other kind of storms. And this it was very exciting. And maybe for answering your question about the cyclogenesis, and maybe we can expand this work by including more predictors, more variables that can characterize this the cyclogenesis, and also the evolution and the fading of the cyclone.
Okay, another question from Giulio. You choose a testing set with a 10-year period, which happens to broadly coincide with the El Niño signal. Does that matter, given that cyclone behavior strongly correlates with El Niño Southern Oscillation?
Okay, interesting question. And actually, we didn't go through this kind of investigation. And but we focused on the joint North Atlantic and Pacific basin, basically. I know that there are teleconnections or connection among events across the globe, but we didn't investigate this, but it would be an interesting suggestion for future development.
So one way to answer this question might also be associated to the answer to the next question. Do you expect this approach to perform in the same way in other regions, for example, Indian Ocean? And if not, why?
Yeah, okay. We at the beginning of this work, we thought to the first to the detection approach, the localization approach of tropical cyclones to avoid the use of deterministic tracking schemes based on threshold, okay? Because at the beginning, the aim was only to locate the TC center position of TCs. And we considered that region because it is rich of tropical cyclones event. And I believe that we didn't try to relocate this approach to other areas, but if we have the input predictors, so we have basically RFI maps, we can extract the 6 predictors from there, creating pages and feed to the network to see how it performs. One major concerns can be about the maybe different values of the variables that may differ from basin to basin. So we should check this, but it's very interesting. It is a challenging point.
Okay, another question from Giacomo Giuliani. Hello, Gabriele. Thank you for your presentation. Regarding the hybrid tracking scheme, you said that a reconstructed trajectory to be valid has to last at least 3 days. I was wondering how the method could be applied for tropical storms that last 3 years at most.
Okay, so basically we rely on a deterministic trigger for a reconstructing trajectory. It is the one from Zhao and Scoccimarro. And actually, we used that thresholds with that values, that variables, and so this is basically I don't know if I can say that I can say this, Enrico, it's a limitation of the deterministic tracking scheme.
But I mean, this is a way to reduce one of the methods we use to do not take into account storms that do not develop in tropical cyclones. I mean, if there are no TCs lasting 2 days only, that's also the reason why we use this way to filter out disturbances. We have still 3 minutes. Wow, many other questions coming at the last minute, guys. Andrea Ficchi, thank you for the talk. Did you compare your machine learning based for TC center localization with other methods using the same fields? Example given by finding the minimum value of wind speed or minimum sea level pressure or the maximum value of cyclogenic vorticity.
Okay, so no, actually we or so in the sense that we compared our machine learning based approach with other deterministic triggers from the literature. They are 4 triggers, and I this one, okay, this that I put in this figure. But
so these are different tracking methods applied to the same data set.
Yeah.
Naim Jafar, what do you think to improve the accuracy of the model?
Very interesting. It's an open question, actually. And so as I said before, so we can try different architecture, also following the suggestion of Giulio, because the VGG is, to me, a very basic convolutional architecture to extract some meaningful information. But we can try in training to train different machine learning models, other architectures, and maybe extending the pool of models participating in the machine learning ensemble, maybe from 13 to 15 and so on. And so, or trying to fine-tune the machine learning model we have right now.
Okay, so we still have 1 minute. If I can, I wanna make a question or suggestion, whatever. As you probably know, the main problem that we have when we want to track tropical storms in our not only reanalysis but also in our model output, and when we want to do that in a multi-model and multi-scenario and multi-member way, there is the problem of the cost of the tracking, not in terms of computational cost, but we need a lot of space because we have to store 6-hourly data to download and to gather 6-hourly data from many models in over different level, etc. So do you think that this kind of approach that you are proposing here should be something going in the direction to reduce the amount of work that people is supposed to do to have tropical cyclone tracks done from models or reanalysis? I mean, is there any way to put your tracker eventually online in the models just to get the output directly as in terms of tropical cyclone tracks directly in the model output, independently on the time horizon we are considering? I mean, climate model output for whatever is the time horizon you are working on.
Yeah, that's basically the goal, not of the entire hybrid tracking approach, but the goal of the localization approach we proposed, because we are decoupled from the time dimension. So the time is implicit in this work. So just if we just have the same variables, or maybe we can try with a lower number of variables, we can feed the neural network with the variable coming from let's say a model, a numerical model simulation, and to predict the locations, right?
Okay, thank you. Well, there is another question coming. Let's try. Still from Naveen Raghu. When evaluating the events falling under false alarm, did you find any common physical characteristic of the events which the machine learning model fails to learn or ignores?
Okay, about false alarms. As you can see here, table 2, column false alarms. Our approach has a high number of false alarms. But if you think, so false alarms are good because in order to reconstruct trajectories and to match trajectories with observation, we want to have let's say a particular number of false alarms, okay? Because we must have a number of tracks in order to compare with observation, right? But when we compare with observation, many of them result to be a false alarm because they don't have a counterpart in the observations. And we didn't investigate the physical characteristics under these false alarms situations, but we can investigate in future developments at this point.
Okay, so Gabriele, thank you very much. Thank you, everybody. I think that it was a really successful meeting, and well, I have probably this is something that I have to know when it is the next one, but you will receive a message regarding the next webinar soon. Thank you again.
Thank you. Thank you very much.
Thank you, Gabriele. Bye bye.
Thank you, Enrico. Bye. Thank you, everybody.